Morning to you all. I welcome you all to this 4-week MOOC course on analog electronic circuits. The prerequisite to learn this course is fundamentals of electronic devices and circuits. Specifically, the operational principle of PN junction diode, Zener diode, bipolar junction transistor, field effect transistor. And in this course, we'll see the frequency response analysis of BJT and FET amplifiers. To begin with that, we need to know the behavior of frequency response analysis of passive circuits. So in the first lecture, we'll see the frequency response behavior of passive RC circuits. So the first circuit is RC low pass filter. R is the series element, capacitor is the shunt element. We are taking input across the capacitor. So we'll come to know this is a low pass filter after seeing its behavior. So we'll start with that. We'll apply KVL at the input side. Vi of t is equal to R into I of t plus 1 by C integral of I of t dt. Applying Laplace transform to this equation, Vi of s is equal to R into I of s. Integral equation Laplace transform is 1 by s. So here 1 by Cs I of s. We'll take the output across capacitor. So V naught of t is equal to 1 by C integral of I of t dt. Applying Laplace transform to this, V naught of s is equal to 1 by Cs I of s. From equation 2, I of s is equal to V naught of s into C of s. Substitute I of s in equation number 1 gives Vi of s is equal to R into V naught of s into Cs plus V naught of s. Taking common V naught of s in this equation, V naught of s into 1 plus SCR is equal to Vi of s. Generally, the transfer function of the system is called the transform of output divided by transform of input. Here, Laplace transform of output divided by Laplace transform of input. So, H of s is equal to V naught of s divided by Vi of s is equal to 1 by SCR plus 1. Rearranging this equation, giving to 1 by RC divided by S plus 1 by RC. In general, the transfer function contains a numerator and denominator. If we equate a numerator polynomial to 0 and it gives roots of the polynomial, those roots are called zeros of the transfer function or zeros of the system. Similarly, if the denominator polynomial is equated to 0, roots of the polynomial are called poles of the transfer function. So here pole is at s is equal to minus 1 by RC. If you apply inverse Laplace transform to the transfer function, gives the impulse response of the system. The analysis is not shown here, but h of t is equal to 1 by RC e power minus t by RC u of t. U of t is unit step function. Substituting s is equal to j omega in the transfer function is the substitution from Laplace domain to Fourier domain. So h of j omega is equal to 1 by j omega RC plus 1. So in place of omega, we substitute 2 pi f. So h of f is equal to 1 by j 2 pi f RC plus 1. Making a substitution f1 is equal to 1 by 2 pi RC in this equation finally gives h of f is equal to 1 by 1 plus j f by f1. This is the standard form of first order passive low pass filter. So we'll take the magnitude response and phase response. Magnitude response is magnitude of h of f is equal to 1 by under root of 1 plus f by f1 whole square. Generally, if we have a plus jb, the magnitude is under root of a square plus b square. The phase is tan inverse of b by a. But here the polynomial is denominator. If we move phase from denominator to numerator, it will become minus. So angle of h of f is equal to minus tan inverse of f by f1. We can see here the two plots. The first one indicating the magnitude response, second one is indicating the phase response. In this equation, if you substitute f is equal to 0, this equation will become, the magnitude become 1. And if you so on substituting f value, gives a response like this. So yet f is equal to f1, 1 by 1 whole square is 1, 1 plus 1 is 2, under root 2, that is 1 by root 2. The value is 0.707. And you go on substituting the value, it gives diminishing response and it leads to 0 at f is equal to infinity. Similarly, the phase response. So from this point, we can say that it is a low pass filter. The frequency response, the magnitude of the transfer function of the filter is a decreasing after f1 and leads to 0. Similarly, the phase response. So this is RC low pass filter frequency response analysis. Similarly, RC high pass filter. Capacitor is the series element. Resistor is the shunt element. Continuing the same analysis as done for the RC low pass filter, KVL at the input side of the circuit. Vi of t is equal to 1 by c integral of I of t dt plus R into I of t. Applying Laplace transform to this equation, Vi of s is equal to 1 by Cs I of s plus R into I of s. And taking the equation for the output, R into I of t is equal to V naught of t. Applying Laplace transform to this, V naught of s is equal to R into I of s. Continuing, I of s from this equation, I of s is equal to V naught of s by R. Substituting this equation in equation number 5, Vi of s is equal to V naught of s divided by R into C into s plus V naught of s. Taking common from this polynomial, V naught of s is equal to 1 by RCS plus 1. And rearranging this equation to get the transfer function, we will get 1 by 1 plus SCR plus 1. This can be written like S by S plus 1 by RC. This having both a numerator and denominator. Previously, numerator is a constant, but here numerator is a function of S. So equating numerator to 0 will give S is equal to 0. So 0 at origin. And equating denominator to 0, S plus 1 by RC is equal to 0. That is S is equal to minus 1 by RC. 0 at origin, pole at S is equal to minus 1 by RC. From signals and system analysis and control system analysis, if pole of the transfer function lies on the left half of the S plane, we'll say the system is said to be stable. So the both low pass filter and high pass filter having poles at S is equal to minus 1 by RC, meaning that these two systems are stable. And its frequency response. You can get h of t. The discussion is not shown here. You can try it. H of t is equal to del of t minus 1 by RC e power minus t by RC into u of t. As a similar way, substituting s is equal to j omega to make it from Laplace domain to Fourier domain. So h of j omega is equal to 1 by j omega RC plus 1, substituting omega is equal to 2 pi f and making substitution f2 is equal to 1 by 2 pi RC, we'll get h of f is equal to 1 by 1 minus j f2 by f. This is the standard form of high pass filter transfer function. So similarly, we can get the magnitude response. Magnitude response is 1 by under root of 1 plus F2 by F whole square, phase response, tan inverse of F2 by F. So continuing with this plot, you'll get this magnitude response and phase response. Magnitude response is increasing and ends at 1. Phase response you can see here. So similarly at F2, the magnitude is 0.707 times the highest value. So from this point we can say it is a high pass filter. So RC low pass filter we have seen, RC high pass filter we have seen. These two form basis for the discussion of frequency response analysis of BJT and FET circuits. We'll continue this discussion actually. So, if two low-pass filters are cascaded, one is low-pass filter with the cutoff frequency F11, another cutoff frequency, another low-pass filter with the cutoff frequency F12, then what is the overall cutoff frequency of this cascaded system? That is F1 is equal to minimum of F11 comma F12. If two low-pass filters are cascaded, the overall low pass filter with the cutoff frequency F1 is equal to minimum of F11 comma F12. Similarly, if two high pass filters are cascaded, one is with the cutoff frequency F21, another is cutoff frequency F22, then overall cutoff frequency F2 is a maximum of F21 comma F22. Diagram 3 is a very important one, which is exactly resembles in frequency response of BJT RC coupled amplifier, FET and RC coupled amplifier. You can see here, first one is low pass filter with cutoff frequency 1 megahertz, indicating that it passing the frequency starts from 0 to 1 megahertz. Eliminates the frequency components from 1 megahertz to infinity. So output of the low pass filter contains only 0 to 1 megahertz components only. From that, it is given as input to the high pass filter. High pass filter with the cutoff frequency 1K means it allows frequency components from 1 kilohertz to infinity and eliminates from 0 to 1K. So already the output of low pass filter contains only 0 to 1 megahertz, from which high pass filter is allowing from 1 kilohertz to 1 megahertz. So it is a band pass filter. It is a band pass filter. Similarly, if I reverse the above diagram 3, first having high pass filter with the cutoff frequency 1 megahertz, low pass filter with the cutoff frequency 1 kilohertz. Imagine the analysis and it is all reject filter. It rejects all frequency components. And I want to make a clear note here is that the active devices BJT and FET without external capacitors is considered to be as a low pass filter because of internal capacitors. We'll see actually the complete internal diagram of BJT and FET in the next sessions. So in BJT and FET RC coupled amplifier can be viewed as a diagram 3. LPF, the low pass filter is due to internal capacitors, high pass filter is due to external capacitors. So this is the end of lecture 1. We discuss the frequency response analysis of both RC low pass filter, RC high pass filter, and its behavior is perfectly useful in the analysis of all discussion of BJT and FET